Let's solve counting point mutations, the next challenge in Rosalind's bioinformatics stronghold. The problem statement says, given two strings S and T of equal length, the Hamming distance between S and T, denoted like so, is the number of corresponding symbols that differ in S and T. Given two DNA strings S and T of equal length, return the Hamming distance. Right, and basically, as you see here in the sample data set and the sample output, you're essentially just counting the number of different differences between these two DNA strands taken from different genomes with a common ancestor, right? And then you're simply just returning the output, and I believe it's indicated by here, right, where it's point it's different, it's not the same. And it's important to keep in mind that the Hamming distance is only defined for the sequence of equal length as given here, right, which is an important factor to consider when implementing this particular problem. The solution for this particular problem is relatively easy. We're simply just going to write a for loop and then just comparing those two different DNA strings. So in this case, for example, at that given index for G, which is index 0, since that's G for the first DNA string and C for the next DNA string at index both at index 0, we're simply just going to implement a count variable that's just going to increment as we iterate through that n length of that given DNA string. And this pattern occurs more, which should result in the desired output. The programming platform used to solve this particular problem is Replit, and the language is Python. But keep in mind, you can use any language, any platform, as long as you submit the right formatted solution that Rosalind does require of you. So in this case, we're going to write the count point mutation function, but first let's define two different variables in this case, which is going to hold the first DNA string in this case, and then the next, right? So let's just copy. This is from the sample input from the given problem that was given to us. I'm just going to copy this next one, right? You can turn that into a string. Then now we're simply just going to write a function which is going to be called count point mutation, passing those two variables as arguments in that given function, right? Then now let's say count point mutation, passing in the same arguments, making sure that, and then we're going to return the print count, right? As mentioned before, we're going to implement a, or let's say have a variable that holds a count, and then increment that whenever we find sort of differences between these two DNA strings that is passed in this given function. So now we're just going to use the first DNA string. Keep in mind, you can use which one you'd like to use. But at the end of the day, they are going to have equal length, so you can use either one. In this case, I'm using the first one as a reference string. And then at that given index I, and this is usually the relational operator. So in this case, this actually means not equal to. So if you were to say, let's say, find the count for the number of equal sort of index values for a particular given string, then you'd have to say that case two equal signs. But in this case, we're saying not equal to, right? And then we're simply just going to increment that count. Then now let's see. This should return the right value, which is going to be 7, as seen here. Now I'm simply just going to download the data set, making sure how to see. Go back like so. Then now I'm just going to copy the txt file information in, and keep in mind, you can technically write this sort of implementation in such a case where you're only reading the txt file, but in this case I'm just going to simply cut and paste, and it should return the right value, like for me, at least in my case, which is 478. And submit that. Right, there you go. And then next, I'm just going to briefly mention that the time complexity for this particular problem is O of n, given that where n is the length of the string, and space complexity is constant, which is O of 1, because we're not really storing anything in this particular case.